into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the Sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course. What would happen to you if you fell into a black hole? The experience of time is different around black holes. From the outside, you seem to slow down as you approach the event horizon, so time passes slower for you. At some point, you would appear to freeze in time, slowly turn red, and disappear. While from your perspective, you can watch the rest of the universe in fast forward, kind of like seeing into the future. Right now, we don't know what happens next, but we think it could be one of two things. One, you die a quick death. A black hole curves space so much that once you cross the event horizon, there is only one possible direction. You can take this literally. Inside the event horizon, you can only go in one direction. It's like being in a really tight alley that closes behind you after each step. The mass of a black hole is so concentrated, at some point even tiny distances of a few centimeters would mean that gravity acts with millions of times more force on different parts of your body. Your cells get torn apart as your body stretches more and more until you're a hot stream of plasma, one atom wide. 2. You die a very quick death. Very soon after you cross the event horizon, you would hit a firewall and be terminated in an instant. Neither of these options are particularly pleasant. How soon you would die depends on the mass of the black hole. A smaller black hole would kill you before you even entered its event horizon, while you probably could travel inside a supermassive black hole for quite a while. As a rule of thumb, the further away from the singularity you are, the longer you live. Black holes come in different sizes. There are stellar mass black holes with a few times the mass of the Sun and the diameter of an asteroid. And then there are these supermassive black holes which are found at the heart of every galaxy and have been feeding for billions of years. Currently, the largest supermassive black hole known is S50014+81, 40 billion times the mass of our Sun. It is 236.7 billion kilometers in diameter, which is 47 times the distance from the Sun to Pluto. As powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To understand how this works, we have to look at empty space. Empty space is not really empty, but filled with virtual particles popping into existence and annihilating each other again. When this happens right on the edge of a black hole, one of the virtual particles will be drawn into the black hole and the other will escape and become a real particle. So the black hole is losing energy. This happens incredibly slowly at first and gets faster as the black hole becomes smaller. Black holes are one of the strangest things at the mass of a large asteroid. They don't radiate at room temperature. When it has the mass of a mountain, and what happens if you fall into one? And in the last second of its life, the black hole radiates away with the energy of billions of nuclear bombs in a huge explosion. Stars are incredibly massive, incredibly slow. Mostly hydrogen black holes we know might take up to a good old year to evaporate. This is so long that when the last black hole radiates away into helium, releasing a tremendous amount of energy. The universe will become uninhabitable of radiation pushes against gravity. This is not the end of our story. There are loads more interesting ideas about black holes. As long as there is fusion in the core, a star remains stable enough. A big thanks to Fraser Cain. Stars have way more mass than our own sun. The heat and pressure we've made the core allow them to fuse heavier elements until they reach our Patreon page. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The universe, the core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light. Where the play of the universe unfolds. But space isn't a fixed stage, and time doesn't tick the same for everyone everywhere. In short, they're relative. Matter bends space, and bent space tells matter how to move. Put some stars and planets on the stage, and it sags underneath them. That misshapen stage, with all its little warps and dips, gives us gravity. Black holes do not just bend the stage, they're like trapdoors, places with so much mass that the universe formed a no-go zone where the rules change. Most black holes form when very massive stars die. We explained this process in detail in our neutron star video. All you need to know now is that in the final moments of really massive stars, their insides implode at nearly a quarter of the speed of light. This packs so much mass so close together, creating something so dense that it sort of breaks the stage of the universe. A black hole with 10 times the mass of the Sun would be barely 60 kilometers across. If you look directly at a black hole, it looks like nothing. The space under their control is blocked by an invisible, one-way border called the event horizon. The event horizon forms a shell around a region of space that, once entered, is shielded from the rest of the universe forever. Because the black hole trapdoor deforms space so much, not even light can escape it. And with nothing escaping to transfer information from the inside, it's impossible to tell what it really looks like. We can still observe black holes because of their effect on matter. Things can orbit black holes just as they can orbit the Sun or a planet. Many black holes have disks of matter orbiting outside the event horizon. This matter can become incredibly hot, as close orbits can speed this matter up to half the speed of light, and tiny amounts of friction and collisions between particles heat them to 1 billion degrees, making the space around these black holes, ironically, incredibly bright. What would happen if you were to try to get close or even inside a black hole? First of all, you'd see the strangest funhouse mirror in the universe. Matter isn't the only thing orbiting a black hole. Gravity is so strong near them that light can orbit too. If you hovered just outside the event horizon, at the photon sphere, in any direction, you just see yourself. Straight ahead would be the back of your own head, as light from your back travels around the black hole to your eyes. Gravity also alters the passage of time itself. The stronger the gravity, the slower time passes. While you watch the universe above you speed up, those far away will watch you in slow motion. If you chose to fly away from the black hole, you might find that eons have passed for the rest of the universe, a freakish one-way time travel trip to the future where your loved ones are long dead. But getting close to a black hole can be incredibly dangerous. A painful death by spaghettification awaits you. Because your feet are closer to the black hole than your head, they feel a stronger pull of gravity enough to pull you apart. As you descend, it gets worse. The pulling gets stronger, your body squeezed thinner and straighter until you've been reduced to a thin stream of hot plasma, gobbled up in one final slurp, never to be seen again. Spaghettification is only a risk with smaller black holes since they have much smaller radii. If you go to the center of a galaxy and find a supermassive black hole, you might be able to experience crossing the event horizon. As you approach the event horizon, a distant observer would think they never saw you enter it, seeing you stop and fade. The last light you emit trickling up and out away from the event horizon. Meanwhile, from your perspective, the void of the black hole rises up to meet you as light from fewer directions can reach you. The blackness envelops you until your only view of the universe you left is a tiny spot of light. Here, inside the event horizon, space and time are so horribly broken that real time travel is possible, so it's probably a good thing that nothing gets out. If anything could escape, it could create all sorts of time travel paradoxes and issues that break the universe. As scary as the event horizon is, it keeps us safe from that drama. Whether you have survived this long doesn't really matter, as now there's only the certainty of crushing death in your near future. Inside the event horizon, space-time itself is so bent and warped that whatever direction you move here, every forward you go leads only towards the center of the black hole. Trying to go in any direction only brings you to the center faster. To survive the longest, you must do nothing. In the center of the black hole, we find the singularity, a single point with all the matter that has ever crossed the event horizon, all crushed to a point infinitely small. There is no memory of the things that made it, as stuff disappears down the black hole trapdoor forever. The singularity makes all things equal. This actually breaks the universe in really cool ways. We've made a video about this problem if you want to learn more. But in a nutshell, everything that comes too close becomes black hole matter concentrated at the singularity. This lack of a memory of its past means that a black hole has only three properties: its mass, spin, and electric charge. Everything else is lost. They're a lot like fundamental particles in that respect. This actually means that every single black hole in the universe is the same. Sure, their mass is different and some spin faster than others, but if we were to put all the singularities into a magical physics museum, they'd be identical, like electrons. But just like fundamental particles, the properties of singularities are the best ways we can describe them on paper, rather than an accurate representation of reality. Our current theories about the universe, namely general relativity, are just not able to describe or explain them. The curvature of space becomes infinite, density becomes infinite, and our rules just don't make sense. The singularity has no surface or size, something like a divide by zero error in the universe. So singularities might not even exist, or be completely different things. But this is all we know right now from the best prediction we have from our best current theory of space-time. Also, basically everything you've ever heard about black holes, even in this video, is about theoretical black holes that aren't spinning because their maths is so much easier. But since black holes were born from dying stars that were spinning extremely quickly in their final moments, as far as we know, all black holes in the universe should be spinning right now. At incredible speeds too, up to 90% of the speed of light. This means that in reality, black holes are even more screwed up than they usually get credit for. The singularities of rotating black holes are even wilder. The rotation causes them to swell outwards into a sort of ringularity. This rotation is so powerful that space itself is dragged along. This creates another region around spinning black holes called the ergosphere, where it's impossible to stay still no matter how hard you try. Like a rushing whirlpool of space-time, the tide is irresistible, and the black hole makes you orbit it whether you want to or not. Okay, So what will happen to black holes as the universe ages and dies around them? Again, we don't know, but we have some ideas based on our current understanding of physics. Hawking radiation. In quantum field theory, the vacuum of space is boiling with quantum fluctuations. These fluctuations are creating matter and antimatter pairs of particles from nothing which only exist for a very short time before annihilating. When this happens near the event horizon of a black hole, one of these particles can fall in, stopping them from annihilating. The escaping particle is Hawking radiation. Ultimately, the mass of this particle must come from the black hole, so over eons black holes will shrink and radiate away. Hawking radiation is not the stuff that fell into the black hole, it's new stuff, stealing mass from it. As the black hole shrinks, the Hawking radiation gets stronger, faster and faster, until what's left eventually evaporates in a flash of high-energy radiation.